To speak on the potential of ML, we have Gary Neights. He is the Senior Director, Product Management at Mimicking, who will give us more insights into this subject. Please welcome him with a huge round of applause.
Clicker is, oh, right here. Okay, great. Okay, good morning, everybody. The brain is an amazing organ. It's evolved over the years. It's great at image processing. You can look around, you immediately can categorize and figure out everything that is in, your span of view. You can look at someone's face and see a nuanced reaction and, make decisions. We evolved from, many generations ago to make fight or flight decisions. Is this person going to hurt me, or are they friendly? And what we do with AI and machine learning is we try to mimic that using computers, using computer power to do this better. In some cases, as Neil mentioned before, AI isn't perfect. No computer is as fast as our brains at figuring out everything that's going on around us and making these really quick decisions. But AI can do some things better than we can do. Let me see if I can get the slide up. So, for example, this is an image created by NASA. Now, who here thinks that a person actually snapped this photograph? Has anyone ever seen this? Yeah, no one's raising their hand. So the answer is no. This is actually created. Astrophysicists will look at things like gamma ray bursts, X-rays, neutrinos, gravity waves, and they take all these different types of data. They use computers to put it together to generate an image like this. So this is something that the human brain cannot even put together on its own. It needs to do it accurately, it needs a lot of inputs and computational power. When I think about my car has 4 cameras around it, one on the left side, one on the right, front and back. It also has software that fuses that together, so I can get like a top-down view of my car. I can rotate the image, and that's something that some people can do with their brains. Not everybody can. That requires a lot of computational power. Self-driving cars, like I have in my car, it'll keep me in the lane. It'll have the adaptive cruise control. But 5 years ago, companies were saying, hey, self-driving cars are right around the horizon. What they're finding out is that self-driving cars really might not ever get there because there are so many nuanced edge cases that a human brain can solve and artificial intelligence can't solve. So I think, as we get into this presentation, the thing that we want to think about is like where to apply AI and machine learning. I'm not really concerned at this point in my life about like the Borg taking over, working with it, that you're going to have some massive Watson thing out there that can figure everything out and control us. There are just so many like limits to machine learning that I think the key is to figure out where to use it. So let's see. Is it possible for me to control the slides so that when I click, they show up? Thanks. Okay. So my name's Gary Neights. I'm a Senior Director of Product Management at Mimicking. And what I want to do today is talk about some very practical applications of machine learning. So I'm going to give a very quick introduction to the company, give some examples. And Neil and I did not collaborate on this, but my first example is supervised machine learning. And my second example is unsupervised machine learning. And then after going through a couple of examples, I would like to come up with present some conclusions to you, and then hopefully leave time for questions and answers about real-life application of machine learning in the supply chain. So this is an introduction to the digital supply chain, and this is what my company, Mimicking, does, is we will connect an enterprise through cloud computing to their suppliers, their customers, their logistics providers. And we have been around for about 20 years. We were formed almost as a joint venture among large chemical companies, really to automate the supply chains. And so when we use machine learning in the supply chain, it's for dollars and cents, hard dollars. If we make a decision with machine learning or artificial intelligence and it ships a product to the wrong location, That can be hundreds of thousands of dollars. So, our application of machine learning has to be absolutely correct. My main focus, similar to Neil, is on the order-to-cash side of things related to customer demand ingestion. This just talks a little bit about the fact that we're doing this worldwide, and we interconnect most of the large global manufacturing companies. And we're using machine learning and computational power to make supply chains more efficient. These are just some examples of our customers and industries that we serve. So pretty much large swaths of the economy to keep products flowing onto grocery shelves, into car dealerships, keep chemical plants, keep energy running. So the first machine learning example I'd like to talk about is document conversion. And Neil gave the example of using supervised machine learning to categorize cats and dogs. I think that was it, right? Yeah, cats and dogs. And so we're using the same type of machine learning using a neural network to train a purchase order, which you can see up here, and have it go through a neural network and accurately convert the different fields of data that are on that purchase order into the right field so it'll flow into an ERP system, an SAP system, or Oracle system accurately. So you might think, hey, that's a pretty easy problem. You can upload a resume into a database and it takes the name and puts it in the right field. It takes the address and puts it in the right field. It puts your experience in the right field. But when you get into something like purchase orders that are going to actually cause a shipment to occur, where a truck or a rail car is going to be dispatched someplace with perhaps hazardous chemicals, you really can't have any room for error. Or if you detect an error with the machine learning-based system, that you detect it and you can trap the error. So as I talk about this, I'll talk a little bit about pre-processing and post-processing of machine learning. You can't just look at it, it's not magic. It's just like any other computer technique. How many people here have experience with software? I just want to see a rough show of hands. Okay. And so does anyone think that machine learning or artificial intelligence is like this magic that you just turn it on, machine learning, artificial intelligence, tell me what I should do. Go look at the internet and tell me what to do. Some business users actually think that. They'll come up with objective functions like that. Just send a crawler out over the internet and tell me what to make. That a little bit of an exaggeration, but it really is not. It really doesn't operate that way. It's just a tool that goes into a software. So, for example, when it comes to interpreting customer data, they might send their data in a very messy way. So you might train the machine learning so that it is expecting an address to be in a certain place. Well, one day the address might come in and it's 123 Main Street, S-T-R-E-E-T. Next order, they might have a different variation. Street might be S-T-R period or S-T period. Now, when you're interpreting bits and bytes of information, your human brain can see that those are all mean the same thing. But the machine needs to be smart enough to determine there's a slight difference, but I need to normalize those. So machine learning can help with those types of problems. It can grab the street address, for example. It can help convert it into like a code that a computer system can read to make sure the product gets to the right location. And then over time, with even more supervised learning, it can then learn the different variations. But with a lot of these types of tools and techniques, you need a human to basically bring a lot of that nuanced information into the machine learning's thought process. So some lessons learned here, I think related to this process of converting a purchase order that comes in on paper into data that can flow into an ERP system. One of the most important things is to understand what's your objective function. Like, what are you doing? Why are you doing this? What are the most important fields to gather? Because one thing we learned with machine learning and using the cat and dog type of example, in the case of a purchase order, like what are the fields you want to train it to recognize? like the purchase order number, the purchase order date, the product identifier, the quantity, the unit of measure. There's certain fields that are very important to get, but there's other fields that are less important. And the one learning we have is that the more fields that you try to train machine learning in, the less accurate that the machine learning becomes. So if you go from the cat and dog example, where it's like a cat versus a dog, if you tried to use machine learning, cat, dog, elephant, snake, cobra versus garter snake versus rattlesnake versus eastern rattlesnake versus sidewinder rattlesnake, the machine learning actually would end up getting, based on my experience, would end up getting confused. So you need to figure out what really is the important objective function and then tune the machine learning to that. Another component of that is what's the pre-processing and post-processing in machine learning. For example, if I'm going to have a machine learning model interpret a purchase order, well, what if it's coming in Italian, or what if it's coming in Chinese or Japanese? You might have to have different, we learned that we had to have different neural networks set up for each language. And so then, before you get a purchase order in, you have to have pre-processing to determine, okay, what's the language of the purchase order so that I can route it to the right machine learning model. So there's a level of pre-processing before you invoke machine learning if you're building a system. There's also post-processing that we found we had to do with machine learning. After the machine learning algorithm does its categorization, you then have to tune that data so it can flow into the ERP system. So there's quite a bit there that you want to think about. So just think of machine learning as not a magic bullet, it's not a silver bullet, it's one component of an overall system, computer system, to solve a problem. So it really comes down to the objective function. And then I'd say we ran into a customer expectation management issue. When we described a new system as using machine learning, it was a supervised machine learning model, which meant our staff was training the system. And customers, though, when they heard machine learning, thought, oh, the machine is learning on its own. And so when they started putting through documents in the system that the system didn't recognize, that meant they needed to have more supervised machine learning by our team. But the customer had an expectation set that the machine would learn on its own. So you also, if you're using machine learning in a commercial customer or client-facing session, it's important that your salespeople, your engagement staff, actually can set the expectations correctly. Otherwise, customers might misinterpret what machine learning is. So let me just pause there and see if there's any comments or questions on this supervised machine learning. Otherwise, I will next go into a second machine learning example, which is predictive risk scoring. So when we look at supply chain, it's really important to know where might the supply chain be disrupted. So you have different types of disruptions that can occur. One is, based on data. You have data about the supply chain, about historics, which carriers, which plants can produce on time, can produce quality materials. And you can use machine learning to go through that sort of data using, in this case, we're using Bayesian math. It's a unsupervised machine learning model that basically uses mathematical techniques to get smarter and smarter with each set of information that's passed into the model. There's another type of risk, though, which is it's more like unforecastable risk. And so in this case, it could be things like COVID, for example, where COVID is causing a number of ports to lose their workers. Therefore, you have enough ships, you have enough crews on the ships, but there's not enough people to load the ships. So that's a supply chain disruption that really would be hard to predict with machine learning, but it's a type of supply chain disruption that we want to present through the same interface to a user, because the user doesn't care what's the mechanism of determining that there's a risk. It might be coming from machine learning, Bayesian math, or it might be coming from a data feed that says the port of Haiphong is having a slowdown due to labor problems. So when it comes to movement of materials, then applying those risk metrics to the specific shipment so that people can make decisions at the time of need. This gets back to, I'll keep repeating this, the objective function. What do you want the machine learning, the artificial intelligence to do? In our case, it's to allow a worker or a computer system to make a decision around how to route material better or how to get new transportation assets. So it's really about presenting the information so people can make decisions. And sometimes this can go down to the more of a palette level. So in this case, we're mixing the machine learning predictives with also just descriptive information about the materials being moved. But this slide here shows predictive risk scoring, and this is coming from the unsupervised machine learning, where basically all the data for shipments going from this location to that location, what's the product, what's the carrier, what's the time of the year, all of those characteristics are going into a big mathematical model. We're calling it machine learning now. I learned about this in business school many, many years ago before we had cloud computing. It's just using math, basically. It's just crunching numbers mathematically, using the cloud resources, the increase in computational power that we have, and also the increase in networked data. The type of machine learning that we can now do was not possible because you couldn't get the data interconnected. Neil, I think you mentioned this as well earlier. We see the same thing. I mean, one of the big lessons learned for us as a network that interconnects lots of large global manufacturing companies is that having access to the data is actually one of the really key things. You can get all these data sets and correlate them. Now that you have all that data correlated, then you can apply these mathematical models like machine learning, artificial intelligence to them. Some lessons learned. Again, the access to the data is really the hard part. Machine learning or any type of mathematical or computer technique can crunch through it. Another thing is what to do with the machine learning outputs, is hard. If you're dealing, like that picture that I showed at the beginning, if that was off a little bit, if the one star was off a centimeter to the right, does it matter? No, it's just a picture. It's the same thing with a lot of machine learning and artificial intelligence that's used in drug discovery, or if you're using it in marketing, you're just using it to, a human being's gonna then post-process it and apply their own standards to it, their own litmus test. And so it's not that big of a deal. But when you're using machine learning and artificial intelligence to drive business decisions, that the wrong decision can ship a hazardous material to the wrong location, you have to make sure that you have everything totally trapped. So, or if you simply send the wrong quantity, you could shut a plant down. So it's not even the value of what you're shipping in supply chain, like a car. A car is made up of 10,000 parts. Well, you could have a 20-cent component that if it's missing from that car manufacturing process, could keep a $50,000 car from shipping because they don't have enough of this one part. So with supply chain, you really want to make sure that you get it right. And so you need to make sure that when you're using machine learning in that type of environment that you're always right. You can't say, this has a 87.5% chance, so we're going to go with it. Plants need to run at 3, 5, 6 nines. So just to finally conclude, the objective function is really the key, in my mind, to figuring out what is it you want to accomplish from a business standpoint, and then determine, is machine learning the right tool? Access to data is a very important key challenge. Getting the data normalized so you can correlate it. Figuring out how to derive the value from the outputs and values that matter to your customer, whether it's an internal customer or an external customer that's going to pay for it. And then finally, AI and ML is not perfect. It makes mistakes, and it actually gets overloaded. Going back to my initial machine learning example of converting a purchase order into data that can flow into a SAP system or an Oracle system. we had been told by the data scientists that as we added more and more samples to the neural network, it would get smarter and smarter and smarter and start to generalize. And so if you added like 10 million samples, I mean, that's too many. If you added like 20,000 samples, that you could stop because it then learned enough that anything new would fall into it. We actually found just the opposite. As we increased the number of samples that we put into the model, after a while, it's kind of like our own brains. You know, your brain can only hold so much. So a new bit of information comes in, and it kind of like pushes something out the back end. And we started to find that as we increased the scope of it, that adding in a new sample, maybe when you first added it in, the machine learning performance coming out of it was good. But then you added 10,000 samples behind it, suddenly that one that used to work, the learning that took place in the mathematical neural network actually made some of the earlier samples start to become less accurate. So we actually learned, at least with this neural network that we used, that it behaved almost like a human brain. You know, it got overloaded and, you know, it forgot things. So it was kind of like, you know, poetic. So that's pretty much the end of the presentation. Hopefully we have some time for questions here. Yeah. Mm-hmm. Yep. Rather than trying to generalize it some more. So probably they could, you know, if I talk about maybe like not now, but there are ways to have more data and generalize without having an issue that they can mention again. Yep, and I think you're right. I think there's ways to solve these problems. You just have to identify it and then figure out, like, okay, what's going on with that specific model, and how do we de-bottleneck it and make it smarter? Yep, and to me, no, I think this is a great conversation because it's also sort of like math. Like, you know, I learned math the old way. I memorized my times tables and everything, and I can take any math problem and solve it. My kids were taught math, and they actually would say, hey, the old way is easier to understand, but some of the new techniques they were taught actually didn't work right. So it's like the technique that you use for training, I think, is really key. Any other questions?
If anyone else has questions, we have somebody with a microphone here for you as well.
Yeah. Hello, good talk, thank you. When you talked about the language differences, German, Spanish, and so on, are each of those models, are they pre-trained language models? Is that what it is, kind of like a BERT, or how are you, can you give some more detail on that?
Yeah, so with that, we did a bunch of experimentation. And we first tried taking English documents, German documents, French documents, different languages, put them all into one model, and we found the performance was not good. So then what we did was we split it. And so a document that looked like it was German, okay, we trained that in the German model. The model itself didn't know, the model itself is dumb. It's just looking at pixels. But we made the choice to route all the German documents to the model that we named German, French to the one we named French, English to the ones we named English. Then we started doing some testing, and we did some combination testing. And so, believe it or not, we found that just using those three languages, that the optimal performance came from having an English model and a second model that was French and German. Now that's a little counterintuitive, and I'm not a language expert, but like German is more like an Anglican language, like English. So you would have expected that German and English would have performed better, and French should have been off to the side. But French and German proved to be more accurate together, and English separate. So we learned some things like that just through doing experimentation. Did that answer the question? Okay. I saw another question up towards the front here. Yep.
Any thoughts on the difficulty of unlearning? That once you have all of the data and patterns into your machine learning database, what happens if a condition changes and you need to break that pattern recognition? And can you talk a little bit about that and challenges and things you've learned?
Yep. We ended up doing that when so we started off with our models with, let's just say we were looking for 20 fields of interest. You know, the purchase order number, the purchase order date, the purchase order line number, the product ID, the unit measure, all those. We had a certain number of characteristics. One of the characteristics that really started to confuse the machine learning model was the unit of measure that something was ordered in, which maybe would be a drum, as compared to the unit of measure that it is priced in, that might be kilogram. So the machine learning model would sometimes swap those, and then we had the wrong unit of measure going in. So what we ended up doing after, put some human thought into it, was we decided, let's go ahead and limit the scope of the objective function, and we were only going to go, in this example, for the unit of measure of the product that they wanted in drums, and no longer would we go for try to get the pricing unit of measure. So to unlearn the model, we then pulled that characteristic out of the model. And so now it no longer, mathematically, when we removed it, we basically made a clone. We kept it because we didn't want to have to retrain all these thousands and thousands of documents. Made a clone of the model and deleted it out. And then we measured performance and are moving forward, making that decision. And what that did was slightly changed our objective function, because no longer were we able to get both of those fields, but we were only getting one of them. But we had to make a value-based decision. That's a great question. Here we have a question in the back.
Do you also include any kind of parameters so that when machine learning starts to come up with certain values that they come outside of, say, a set parameter that then is going to kick it out to managerial review so that you don't end up with, 10 million parts being ordered instead of 10,000?
Yep. No, that's another great question, and I would call that the post-processing step. And so we see that at I'll call it like a tactical level. And one thing there might be the machine learning model, we're looking for an integer to come out. But then we find that there might be a space in there, that the machine learning gets a space and maybe an extra character. So instead of 10,000 being 1 followed by 4 zeros, it would be 1, a 0, a space, 3 zeros, and a slash. And so at a very tactical level, where we started to see that, we started putting in field level post-processing, or for dates, looking for certain date patterns. Then at a more strategic level, looking at things like taking a plant address, and the plant might have different unloading points. And so at a big plant like the Exxon Baytown refinery, it probably is like, 20 square miles. And so, it might be the same ship-to location, but it's like this warehouse versus that warehouse versus that warehouse. And so more strategically having processing after the machine learning to make sure that you get it to the right warehouse location, and then that warehouse might have specific parameters. So that was like a broader level that's all part of like what we do as a supply chain network. Did that answer the question? Okay, yeah, feel free to come up afterwards.
We have time for one more question.
Piggybacking on the gentleman's question from the back, our brains are amazing organs. So we know when to raise our hand for help. So, and we know when to escalate things, when we know it is somebody else's decision. So how do we work on these escalations as part of the AI or the machine learning world? You did bring up in your last slide, we can't go with 87.5% acceptance on a car that is missing a critical part. A bolt is not fitted. Yep. It's going to fall apart. So these escalations become really important. How do we train the AI using the machine learning to do these escalations, to behave like our brain?
So the way we tackled it, and it might not be the best way, but the machine learning is actually simply feeding, it's part of a complex system. And so there's a part of the application post-machine learning that traps those things. And so there's a whole alerting framework in there. And one of the things we were really careful on in this purchase order process was to identify different error cases where we want to involve a human being. And so based on the parameters, human knowledge could decide, do I want to set this flow to automatically flow into the ERP system or not? If it's set to automatic, what are the cases that will be escalated out to a human? Additionally, there could be some cases where you just simply know that there's information that the machine learning cannot even get. An example might be a purchase order type. Is this product on consignment, or is this product that's going to be invoiced right away? Just as an example, it's not anywhere on the order, and it's in the CSR's brain. So in that case, they would always have it set as an exception so the CSR could set that. The same thing came down to distribution points in Europe, where sometimes the product would ship from this location versus that location, and it was dynamic, and they wanted to have a customer service representative make that decision. So post-processing, machine learning couldn't do any of that. It's beyond what the objective function for it was. That was part of the broader supply chain application. Well, I'll be around afterwards. If anyone has any questions, feel free to come up and we can chat. Thank you all very much.